Let's dive into one of the sneakiest, most dangerous issues you can run into with Go concurrency, the Goroutine leak. Now, this isn't your classic memory leak. No, this is something different. It's about the ghosts in your machine and what happens when the workers you hire never ever come home. So, picture this. Meet Ethan. He's a developer, and he's just staring at his monitoring dashboard, completely defeated. He's facing a problem that just doesn't make any sense. His service's memory isn't spiking or acting erratically, it's just climbing, steadily, with this terrifying, relentless certainty. So what in the world is going on here? I mean, Ethan's already checked all the usual suspects, right? He's looked for memory leaks from growing slices, he's checked for unclosed files, faulty defer statements, the whole checklist. And everything comes up clean. And yet, like clockwork, the service just keeps bleeding memory. This is the classic sign of a problem that's hiding in plain sight. And that's the exact question his senior colleague, Eleanor, asks him. She tells him, Ethan, the problem isn't in the data your service is holding. The ghost, she says, is in your workforce. And no, she's not talking about his colleagues. She's talking about his Go routines. You see, while Ethan was watching that memory graph creep up, this number was also ticking up. And up. And up. One new Go routine for every single request his service handled. And here's the kicker. None of them were ever finishing their job. This is the source of the leak. To really get him to understand what's happening, Eleanor comes up with this brilliant metaphor that just cuts right to the heart of the problem. She calls the leaked Go routine a zombie worker, and honestly, it's perfect. It's a process that's not really alive, but it's not gone either. It just waits. So, what is a Go routine leak, officially? Well, it's when a Go routine gets stuck. It's usually blocked on something like a channel or a network call, and it simply cannot exit. Now, here's the crucial part. Go's garbage collector only cleans up Go routines that have actually finished. So these zombies, they just pile up, slowly eating resources until, you guessed it, the whole application comes crashing down. This right here, this is the mental trap that gets so many developers into trouble. Ethan, he thought he could just launch a background task, fire it off, and let the main request just move on. But Go really doesn't work that way. Every single Go routine you start needs a clear, defined path to completion. If you forget about it, believe me, it will not forget about you. And the way it fails is so deceptively simple. Okay, so first, a worker Go routine is launched to do some job. Then the main function that started it moves on. Maybe a request timeout was hit, who knows? The worker, it finishes its job and it goes to send the result back over a channel. But here's the critical failure. There's nobody on the other end listening anymore. That send operation blocks, and the Go routine is now stuck. Forever. Okay, so how do we stop ourselves from creating these armies of the undead in our code? Well, the solution isn't some super complex algorithm. It's all about using two fundamental Go idioms to give our workers a way out. We need to give them a tether, and we need to give them a guaranteed exit. Our first tool is the amazing context package. Think of it like a tether or maybe a leash. It lets the main function signal to the worker, hey, we're done here, you can stop what you're doing. The second tool is a buffered channel. This gives the worker a guaranteed escape hatch. It can drop off its result and leave, even if nobody is there waiting for it at that exact second. And here you can see the two patterns side by side. On the left, you've got the leaky pattern. It just tries to send on an unbuffered channel. It's a death trap waiting to happen. But the robust solution on the right is a 1-2 punch. The worker checks the context to see if it should just give up early, and it sends its result to a buffered channel. That combination makes sure the worker never, ever gets stuck. It always has a way out. So, with the fix in hand, Ethan deployed the new code. And the change in the service's behavior, well, it was immediate, and it was dramatic. That slow, relentless memory bleed, gone. The result was just beautiful. The memory usage now behaves exactly as it should. It rises to meet demand when traffic is heavy, but when the load dies down, it levels off. It's stable. And the number of active Go routines now goes up and down naturally, like it's breathing, instead of just expanding forever. The ghosts have finally been laid to rest. So, what's the really crucial takeaway here? It's this. Starting a Go routine isn't some casual thing you do. It's a commitment. You are creating a concurrent process, and that means you are responsible for managing its entire life cycle, from the moment it's born to the moment it terminates. If you only take one single thing away from this explainer, please let it be this rule. Before you ever type go funk, you absolutely must have an answer to the question, under what conditions will this go routine exit? If you don't have a crystal clear answer, you are basically inviting zombies into your system. And this is Eleanor's final piece of wisdom. It's really the perfect summary for responsible concurrency in Go. Don't just send your workers out into the world and hope for the best. You've got to give them a map, give them a signal, and always, always make sure they know the way home.